joined Astronomy Colloquium, you may see quite a number of people who have a name tag on. That means that we run the first Harvard Heidelberg Star Formation meeting. And it's a really great pleasure that on this occasion we even have a speaker for the Joint Astronomy Colloquium from Harvard. It's Karin Öberg. She started her career in chemistry, actually at Caltech, and then she met Jeff Blake and was tracked into astronomy. Now she is actually combining astronomy and chemistry and using chemistry as an interesting tool to study star and planet formation. Karin then moved as a Hubble Fellow to Harvard and then for a short period of time to Virginia and is now back to Harvard as associate professor, establishing a group in astrochemistry and is actually combining observations but also laboratory data and modeling. So very close to my heart and my philosophy to do this kind of science. Today she will talk about the chemistry of planet and star formation, and we're looking forward to an interesting talk.
Thank you. Thank you for that introduction. And thank you for inviting me to give this colloquium. It's, of course, a pleasure to be here, both for this star formation meeting and to be here and speak to you. So the original title that I put in was the chemistry of planet formation, and really how chemistry affects what kind of planets you end up with is going to be the main topic of this talk. But as you'll see, it's impossible to isolate that from the chemistry of the earlier stages of star formation, hence the slight change of title. As usual, this is not work that's done by just me or in isolation, and I've listed some of my main collaborators on this slide, as well as my group members who are now getting established at Harvard. So the lab started being constructed about 3 weeks ago, so I'm not going to show that many new lab results, but instead focus on any observational work we have on this topic. So when I talk about the chemistry of planet formation, I will really be talking about two rather different things. It will be about 50-50 in the talk, how much time I spend on it. So one of them is how chemistry affects really the bulk properties of planets and the planet formation efficiencies and how we could possibly trace that. Also, so using basically both the fact that chemistry affects the physics and that the physics of planet formation affects the chemistry to use chemistry of molecules as probes. The second topic is a slightly more esoteric and complex chemical problem of how you end up, like really what sets the sort of organic content of terrestrial planets, which I'm not going to go all the way to here in this talk, but more how do we know how complex molecules form in planet-forming regions and what processes affect how much organics form and what their compositions are. But as I said, this is closely related to the sort of whole star formation process. Where I'm going to be spending most of the time is in this protoplanetary disk phase, which is where planets form, hence the name. But these disks, they start forming in the protostellar stage, and the protostar forms from the collapse of the cloud core. So when we're looking at the chemistry in these later stages, we do have to be mindful of what is inherited from the earlier stages. So that's going to be one way that we come back to what's going on in the earlier stages of star formation. The other one is that a lot of the chemistry that we're actually really interested in these disks, especially the more complex organic chemistry, turns out to be really difficult to study, mainly based because of the small scales that we deal with when it comes to protoplanetary disks. So in that case, we're actually going to be using these earlier stages of star formation basically as proxies of what we think is going on in these disks. But to start that, I just wanted to talk a little bit about the physics of these disks where planets are forming, since that's going to be very important for the chemistry that we end up studying. So when we look at these disks, they are not just chemically but also physically very complicated structures. You have a radiation field coming from the central star which consists of optical UV X-rays. In addition to that, you have external radiation fields, which are going to vary dependent on whether you're in a low-mass or high-mass star-forming region. I'm going to be mostly ignoring that for this talk, but that is something you have to be mindful of. So that's going to set the basic temperature and radiation gradients in these disks, both radially and vertically. And these gradients are often going to be very steep, which makes it somewhat difficult to model. In addition to that, you do end up having a lot of dynamic processes. One is, of course, is that this disk is forming from the protostellar stage. But also, once you have these disks isolated, these are accretion disks, so you are going to have some accretion flow going inward. There are also disks that transport away angular momentum, which means you're going to have some outward, basically spreading of these disks. In addition to those large-scale transports, you do think you have quite a bit of turbulence that can really move things around both vertically and radially. And that is all going to have an effect for how molecules form, are destroyed, and moved around in these disks. So these are all, there's a great potential, I think, to use chemistry to actually study some of these dynamics. But for this talk, I am going to be completely ignoring them and thinking only in the terms of what the passive disk is doing to the chemistry. So in this much simplified scheme, what we have is just, again, the central star that is setting a radial and vertical temperature structure and a radial and vertical radiation field. So what we should end up seeing, according to these passive models, is if you look in this upper layer of these disks, which should be radiation dominated. So we would expect to see things like atoms, some ions, some molecular fragments like cyan, which is pretty resistant to radiation. That should really be probing the upper disk layer. If we go a little bit further in, we expect to see much richer molecular structures. This is sort of the Goldilocks zone, where things are being protective enough from the UV and somewhat from the X-rays not to be destroyed, but it's yet not so cold that they're completely depleted from the gas phase. If you do move a little bit further in, it does get cold enough that basically all molecules are frozen out into dust grains and they are practically invisible to us. So these structures are actually not readily resolvable in any other way than looking at molecular structures. So you can imagine if we understand the chemistry well enough, we could actually use some of these exact molecules to probe things like the ionization structure, how the radiation is penetrating into the disk, temperature, density structures, and the like. But what I want to focus on right now is what I put here, which is this free set of molecules in the midplane of disks. So if you look at where this starts in the midplane, this is what we typically refer to as a snowline, if you think about sort of solar system. In the solar system, the reason these snowlines is a rather popular concept to talk about is that if you look at it in our own solar system, it's clear that there is somewhat of discontinuity in the solar system between Mars and Jupiter in terms of what kind of planets you have. And if you look at models of the Solar Nebula, this discontinuity in planet kind corresponds roughly to where we think the water snowline was. And the idea is that these bare grains form rocky planetesimals, which form these rocky planets, while the isoplanetesimals, through some mechanism, form these much larger planets. Now, and I think it's important to take a step back and realize that if we, instead of our own solar system, had found the typical exoplanetary system, it is not obvious that we would have put so much emphasis on these snowline locations. But there are actually some, it's probably fortuitous that ended up in a system like this, because there are some good theoretical reason to really want to consider these snowlines and their effects on planet formation. The first one is simply that when you cross the snowline of a very common volatile like water, you get a huge, you get a factor of a few increase in mass typically in most models. So that's already going to bump up sort of your planet formation efficiency a little bit, potentially. Also from experiments and theory, ices should be stickier compared to rocks. I mean, snowballs at least have a shot at sticking together when you throw them at each other, while rocks typically don't. There are some more subtle reasons that people have come up with why these snow lines should matter. I mean, you do expect some basically pressure bumps around these snow lines. How big they are is debated. You can get changes in opacity. And you can have so-called cold finger effects, where basically turbulence draws things down towards the midplane in these outside of the snow line. It draws more material. So if you add all this up, even if not all of them are as effective as predicted, you can easily see that people expect it's not totally surprising that we might get this continuity in planet formation just around the water snow line. But this is all, again, this is very sort of centric, solar system centric, to put so much emphasis on the water snow line. If we look towards protostars, so taking a step back from disks where ices are very difficult to observe, we see that water is not the only volatile species that we have coating grains like this. If we turn, in this case, Spitzer, towards the typical low-mass star-forming region, so or low-mass protostars, so an analog to the protosun, we see these broad absorption bands. I mean, water is definitely there, but we also see absorption bands due to CO, methane, ammonia, methanol, and CO2. So these could all potentially have their own snow lines happening in these disks. So what you really would expect as you look at one of these young disks, as you look at Solar Nebula, you step outwards from the warm sun, is that you add more and more ice on these grains in a very step-like way. And which one of these snow lines that matter the most is going to depend on the detailed temperature and density structure of your disk, and also on your initial chemical composition, and how this chemistry evolved in the disks. So going back to the protostars, you can actually get a pretty good idea of which volatiles that should matter in addition to water. So what's shown here is the sort of median abundances of the volatiles we typically see towards protostars with respect to water. And what should be readily apparent is that CO and CO2 are typically the second most abundant volatiles. As you can see here, the typical value is that they're present about 30% compared to water. But if you look at the distributions as a whole, so this just shows the distribution with respect to the median and the number of sources. So broad distributions means you have a lot of variation with respect to water. Narrow distributions means you don't. And if we look at something like CO, you actually have this tail of very CO ice-rich sources where you end up having actually slightly more CO than you have water. So it's definitely not set in stone that water is always your most abundant volatile, and therefore that plant formation around the water line is the most important one. But so snow lines are important because they affect plant formation efficiencies, we think. They're also important from the point of view of what kind of composition you end up with a planet. There are many different ways you can end up with a planet that doesn't have stellar metallicities. And in an idealized, a toy model, which is shown here, you can see that as you step outwards away from the star, you go through the different snow lines of water, CO2, CO, and at each of these snow lines, you will have a very dramatic change of, in this case, the carbon-to-oxygen ratio in both the grains and in the gas. In the idealized model, where a planet forms at a specific one particular point, and it accretes all its core material from the grains, and all of its gas, all of its gaseous envelope from the gas, and there's no mixing of the two, you see if you can go from having a carbon-to-oxygen ratio of about 0.4 to 0.5 to actually unity. Now, whether this toy model has a whole lot of relation to reality that remains to be seen is something that people both here and that we are looking into further. But I think it's clear that these snow lines are going to change what compositions of planets you have when you think about where the planets are forming with respect to these different snow lines. So hopefully by now you are convinced that these snow lines are important, and actually being able to observe where they are in disks where planet formation is ongoing is something that would be really nice to do. So the way that we can observe gas, I said ice is pretty much invisible to us, but we can observe the gas in these disks, and one example is shown here. So these are observations of the dust in the disk, and then the CO, and this is just the velocity map. These disks are in Keplerian rotation. So this also shows the scale. So you see a scale bar about 150 AU. So if you think about our own solar system, most people would put the CO snow line in our own solar system at around maybe 20 to 30 AU. So the fact that we see CO all the way out to a couple of hundred AU suggests that either our understanding of the CO snow line is totally wrong, or that you have actually CO gas in these disks far beyond where the CO snow line is. I would suggest to do this the latter, which comes out readily if you look at what we think these disks actually look like structurally, which is that you do have this snow line here, but because you also have the vertical temperature structure, you expect to have some CO up here in the atmosphere all throughout the disk. That's something that makes it very difficult to actually directly observe these snow lines, not just of CO, but of any volatile in these disks. If they're always the mid-plane snow line that we care about, is always going to be hidden by this atmosphere. So with that, luckily, there's chemistry. So we started thinking about ways to trace where CO is frozen out indirectly using molecules. And when it comes to CO specifically, the two molecules that we thought might be good, and this is obviously inspired, again, by work done on the earlier stages of star formation. One is NH+. So in all the plots that I show where there's molecules, blue is nitrogen, white is hydrogen, oxygen is red, and carbon is this grayish black. So one of the molecules we thought about is NH+. And the reason for that is that this is a very fragile ion that actually cannot keep its proton very easily at all. So as long as you have any CO in the gas phase, you're readily going to transfer this proton away from the N2 to the CO to form HCO+. But when CO freezes out, you lose this main destruction pathway of NH+, and you expect to build up an observable amount. The other molecule that we thought about was formaldehyde and methanol. The only formaldehyde is shown here. And the reason for that is the main formation pathway of formaldehyde is adding hydrogen to CO that's frozen out onto grains. This pathway does not work in the gas phase. So formaldehyde and NH+. Keep those in mind. So the first thing we did was to go back to try to figure out whether these were actually good tracers of the CO snow line, is to go back to a survey that we carried out in 2009 and 2010 with the sub-millimeter array, where we looked at a bunch of different molecules towards 12 disks that spanned sort of in mass and luminosity and in structure what was known of large and observable disks in the northern hemisphere. So especially we do get a pretty large span in luminosity of the central star, which means that we expect a pretty large range in disk temperature, including disks that are too warm all the way through to have any CO freeze out at all. So if we look at the results of this survey, so this shows the lines that we detected, and as you can tell, I want you to focus on these rows here. And these are pretty much the disks that are cold enough, we think, to have CO freeze out, and these are the ones that are probably too warm to have any CO freeze out going on in them. And if we look at these two molecules, these two lines are due to formaldehyde, this is due to NH+. These are all pretty low signal to noise detections, but in general, we do detect NH+ of formaldehyde in the left-hand part of the plot, and not in the right hand. So this already suggests, or this is consistent with, that these two molecules only show up when you have cold material around. And we claim cold material enough then to freeze out CO. I think the second, more convincing, even again this low signal-to-noise observation of that this might work, is that if you look towards this one disk, HG163296, which is a bit special in that it's actually a rather luminous star, but it has a very massive disk around it, which means that it actually has cold enough material that it should have CO frozen out. If you look at this disk towards, we look at a bunch of different molecular transitions, we generally see this nice peak structure in a bunch of different molecules. But the one molecule where we don't is formaldehyde. And I mean, you probably have to be in a pretty good mood to claim that that's a ring, but it's at least offset emission from the center. And the only way we could possibly model this distribution is with a ring-like structure where the inner rim of that ring corresponds to roughly where CO should be freezing out in this system. But this was pre-ALMA, so pre-ALMA you're not going to do much better than these kind of blob-like ring. So we simulated, if we were right about what this ring should look like, we simulated what that should look like with ALMA, which is shown here. So these are just two different structures, so both fit the data equally well. There's a different kind of sharpness of where this snowline is. And we should see the same structure in methanol and in N2H+, since they all should trace the CS snowline. So I said these were just simulations. We submitted these simulations to ALMA cycle 0 and were denied. We submitted them again in cycle 1 and were denied time again. But little did they know that in another proposal that was targeting a totally different ion, we had actually also managed to squeeze in N2H+, which should show this exactly same behavior. And that disk is TW Hydra, which is very nice because it's face-on, so it's very simple geometry. So this shows the observations of the continuum of the CO. Again, you see CO being very extended. And then of N2H+ over here. And the red dashed line corresponds to what we would expect to actually see the CO snowline in this system. And as you can tell, there is a very nice ring with an inner rim that is very reasonable compared to what CO should be freezing out. And I think it was Alyssa said yesterday, actually mimicking some other of our friends, that it actually seems like chemistry works in tracing structures in disks. So that was very encouraging. And this is just a different visualization of the same phenomenon, building on this workshop. Again, showing this rather poisonous-looking CO snowline, which I think my mother thought it looked like one of these crazy mushrooms or something like that. And, but I think it conveys the message. So in addition to being a cool tool to look at snow lines in other disks, I mean, this is something that could be readily now extended to rather large samples to look at the CO snowline. And with a better understanding of the chemistry, it could also be extended to different kind of volatiles, for example, CO2 and water. This also has some consequences for understanding our own solar system and how it formed. So if you look at simulations of how the outer planets formed in the solar system, this is from the NICE simulation, they are basically predicted to form in a rather compact structure, all well within the CO snowline, assuming that our solar nebula behavior is similar to TW Hydra, which is seen basically as a solar twin. That means that none of them could actually have accreted any CO ice or built up really any metallicity over metallicities in their envelope from accreting CO ice, which has otherwise been proposed as a mechanism to build up some extra carbon and oxygen, in especially Neptune and Uranus. However, what this also shows is that a significant fraction of the comets and Kuiper Belt objects forming outside of these giant planets should have CO ice in them. And this seems to roughly actually agree with observations. So there are some comets that are very CO poor, the other ones that are CO rich. And having the CO snowline basically fall right in the middle of this comet-forming population seems to be in good agreement with that. So with that, as I promised, I want to switch gears a bit and talk about the implications of having these ices in disks for the formation of more complex molecules. So the first thing, though, that for this to be a relevant topic, really, at least for origins of life kind of talks or for terrestrial compositions in general, I think this is the scenario that first needs to be understood. So, and I come to this in a couple of slides, but there are good reasons to think that a lot of the Earth's water was delivered from elsewhere. But elsewhere in the disk, I mean, it might be 4 AU, it might be bodies forming at 10 AU, or it might mean bodies forming at 30 AU. That is not, I'll say, a priori clear. And as we've seen, as we move outside in the disk, we are really going to be changing what the composition of these grains are that then form boulders, that form comets that can seed things like the Earth. If we form fairly close in on the disk, we're going to be completely water-dominated, these grain mantles. We have out a bit, we'll add CO2. We have out a bit more, and we'll add CO. Now, this latter addition of CO is very important because, as I already talked about, one of the things that CO ice does very well is being converted into formaldehyde and methanol, and from there to other organics. So if we want a young Earth to not just be seeded with water, but also with this kind of organic material, then at least some of these comets better have formed out that 30 AU that brought this water to Earth. So the question number one is, can we tell whether things like Earth's sea water, where it actually came from in the disk? So one of the most popular ways to try to date where molecules in the solar system comes from is from looking at their isotopic ratios, and especially the D/H ratio is one of the more popular ones. So this is stuff I took actually from one of Paula's papers. But the basic idea is that to increase your fraction of a heavy isotope, in this case the deuterium over hydrogen in a molecule, it's really only efficient at very low temperatures. And the reason for that is that the two ways to enhance your deuterium fraction in a molecule is through cold ion molecule chemistry, mostly going through this route of basically taking one of your deuterium from Hd, putting it in H2D+, which has a small energy gain, but it is very small, which is why this is only efficient at low temperatures. Otherwise, you'll just go back. And then to go from this H2D+, to put this D+ in other molecules, for example, DCO+. The other way is through grain surface chemistry, but then you actually need to get to this H2D+ as well, and then through the recombination, you form this deuterium atom that then can become incorporated, for example, forming HDO on grains. So in both cases, you do need this cold starting point. And what's shown here to the right are just a few different models, as said from Paula's paper, showing how dependent this ratio of H2D+ to H3+ is on temperature. And that's why we think we can use the D/H ratio in molecules to really look at where in the disk a molecule formed, or even if it formed prior to this formation in that kind of cold material. And if we look in the solar system, this seems to mostly make sense. I mean, where we do, so this shows the D/H ratio in different kinds of solar bodies, or like solar system bodies. So if you look at comets, which should be formed rather cold, they tend to have a high D/H ratio. And then if you go inwards in the solar system, this D/H ratio starts to approach more and more what's the solar value. One of the outliers, though, is the terrestrial or like the seawater here on Earth, which has a DTH ratio that's actually not too far off from that from comets. And the same is true for some asteroids that have this very high DTH ratio. And the idea is that this very high DTH ratio of Earth, that implies that at least some of the volatiles must have come from bodies that formed further out in the solar system. If we look, this is all, though, depends on, let's say, the fossil record in the solar system, and we know things have moved around in the solar system, which makes this non-trivial to interpret. So one of the things we can do now, which is really cool, is that we can go to other disks where planet formation is ongoing. This is again TW Hydra. And look at what the deuterium distribution or the D2H distribution of these different molecules actually looks like there. And the first one that was looked like in great detail was this DCO+. And as you can tell, there is, again, the emission is offset from the center. So that means that the DTH ratio is increasing as you go outwards in DCO+. It makes perfect sense according to these models. Then we also, maybe we should have stopped there, but we didn't. We went and looked at another molecule. So this is DCN. And here you actually see that it is not offset from the center. We actually have a perfectly centrally peaked distribution, which suggests that at least on these spatial scales, there's no hint of that this has a cold chemistry origin. This should not have maybe been as surprising to you as it was, since this DCN has a second pathway that goes through another ion, CH3OH, which actually starts to fractionate at a much higher temperature, all the way up to 50 Kelvin compared to DCO+, which goes through H2D+. But still, what this shows already is that deuterium fractionation is not necessarily a sign of very cold chemistry. It can definitely be a sign of, let's say, moderately cold chemistry as well. And I think to use this deuterium fractionation to infer the history in the solar system, we definitely need to have a better understanding of how this happens in different molecules, and also how different molecules can then interact and move deuterium from one to another. This is something that actually I think we will have a better handle on in just the next year or so. They have started acquiring data for us, looking at 6 different disks in 4 different molecules. The only one that we're really missing that we really would like to have is water, but that's because water is very difficult, and I think we're probably going to have to wait with seeing that in disks until we have complete ALMA. But in the meantime, we should at least get the DTH fractionation pattern in disks in a bunch of different molecules just in the next year or so. So while we're not really there yet, that we can date exactly where something comes from based on their isotopic fractionation pattern, I think we're definitely making progress on that. So putting that to the side, as we will hopefully be able to figure that out. The next thing we then want to know is, okay, if you are at a specific radius, a specific temperature, what kind of molecules will your ice actually be made up of? I would say that's, if you want to be able to predict what ends up on something like the Earth. Now, again, so the framework that we are thinking within here is that of ice chemistry. So we think that most of these molecules are actually going to form in the ices. And the way that they are most likely going to form, this is based on a combination of laboratory experiments and theory, is that you start with your simple ice, so which is going to depend on the snow lines. And you dissociate these simple ices into even smaller fragments, and then you have them recombined to form larger molecules. And if these molecules get out into the gas phase, we can actually observe them and tell what happened. What would be really great is if we could go now to protoplanetary disks, observe the distribution of these organic molecules, and based on that, tell at which radius you will have certain organic molecules forming. This turns out to be much harder than we had hoped for. And even now, with cycle 0 of ALMA being complete and cycle 1 being sort of halfway there, there's still no one has been able to detect methanol in these disks. And that means that even with full ALMA, methanol I really do hope that somebody sees in cycle 2, because otherwise it would be very sad. But it means that it's going to be difficult to go beyond methanol, at least in more than a few disks. And that means we need an alternative way to figure out how this chemistry is evolving, that this complex organic chemistry is evolving in disks. So one way is to go through laboratory, and I'll come back to that briefly towards the very end, and try to figure out these different microscopic processes well enough that you can put them into a model and then have confidence in this model and predict what's going on in your disk. The other method is to go to another place in the stellar medium, in this case protostars, where we actually can observe these complex organics and use that as a template for how this chemistry evolves in general in star and planet-forming regions. And the place where traditionally you have seen a lot of these complex organics is in the inner regions of protostars. In these, especially if you look towards massive young stellar objects or massive protostars, you will frequently find spectra like this. So these are very rich spectra where most of these lines are due to complex organic molecules. Some of them are marked here. So these are all coming from these innermost, very hot regions in the protostars where we have had all this ice chemistry happening, and then all the ice sort of instantaneously sublimates into the gas phase, releasing all these molecules so we can pick them up with milliliter spectroscopy. The fact that they're forming slowly in these earlier phases and then all getting released into the gas phase at once actually makes it very difficult to infer the chemical evolution from this kind of spectra. I mean, you basically just get the endpoint, which is it's not that helpful. And I think one of the really nice things that we realized just during the past couple of years, or a few years, is that these inner regions of both high mass and low mass protostars are actually not the only places where you can observe these complex organics. You can actually see them, at least in some limestone sites, towards the very cold regions as well. So what's shown here is one of these low mass prestellar cores, B1b. And this shows cold methanol emission. And then we simply pointed a thermometer towards sort of the peak of the methanol emission and integrated for a very long time. And what we found was acetaldehyde and methyl formate, so two of the sort of classical hot core molecules. And what this means is, first of all, is that these molecules can form very cold, but maybe more equally important that we can get that into the gas phase cold, which means that we have the potential to study them as they're forming and not just at the very end state that everything comes out. But combining this data with other people's observations of complex molecules at different temperatures, it's also clear that even though you can form at least some complex molecules at very low temperatures, that this chemistry does evolve. So here we're looking at warmer and warmer sources, and here's just one way of comparing the complex molecular composition, in this case focusing on the ratio between these HCl-rich complex molecules over methyl-rich complex molecules. And there are some good reasons why you would expect this inverse trends, but I think the most important message here is just that this chemistry does evolve. And the fact that we can see some of these complex molecules coming off at very cold temperatures means that we can actually observe it as it is evolving. But these are all totally different sources, which means again that it's not trivial to interpret, and you have quite a lot of scatter. So what you would really like to do if you want to understand this chemistry is to go in and look at single sources or samples of sources where you spatially resolve how the chemistry evolves from the cold outer regions in towards the hot core region. With the idea that you should see the same kind of evolution there as you saw between the different kind of sources in the previous slide, as simply these ices become warmer and warmer, enabling more and more kinds of molecules to form before they all evaporate thermally in the center. And what's basically shown here as well is that the reason we do see some of them coming up cold is that you do have different non-thermal desorption pathways of these ices that can be activated long before you have this thermal evaporation taking place. And luckily, nowadays we do have the tools to do that by combining single dish and observations with different interferometers. We use the sub-millimeter array in a couple of different configurations to really get to probe all the different scales towards some of these protostars. So this shows just one example of the kind of data that we saw. And other people have seen similar things, though not necessarily this sort of nicely shell-like. So what you see here is this emission from a bunch of different organic molecules. As you can tell, some of them are very compact. Some of them have this extended distribution. And some here you don't see at all, even though we do actually pick them up with our single dish observations. So these are just they're so diffuse that they're completely resolved out when you look at it with an interferometer. So the first thing that's just telling you is that just when you look at these individual objects, you do have some chemical evolution as you look at this one protostar going from the inside out. This particular protostar was fortunate in that it had it's not exactly a spherical cowl, but it's actually approaching it the most of all our sources, which means that we thought it might actually be useful to just look how the spectra towards the source evolves in shells going outwards from the center. So as this was shown here, that these spectra of one of the methanol lines, so this spectra is just extracted using a 1 arcsecond mask, 2 arcseconds, 3 arcseconds, and 5 arcseconds. And you pick up more and more emission as you make your mask larger, as you would expect for an extended emission source. If you look at the complete methanol spectra, you do see this, they pick up more and more emission with larger masks. But in addition, you see that there are some lines that increase much more compared to others, so especially these ones compared to these ones here, for example. And that's simply due to that these are low energy lines and these are higher energy ones, so that makes perfect sense. If you do try to extract the rotational temperature from these different shells, you do get something that actually agrees very well with an existing model of this source. So model is in red, which comes mainly from dust modeling, and then the methanol rotational temperatures are shown as points on top. So I think it's a sanity check showing that this shell, like looking at the chemistry in shells, actually makes sense. And of course, once you have convinced yourself that that makes sense, you can start looking at also what other molecules are doing. And this shows, I think, one of the clearest examples, methyl cyanide and methylacetylene. Like I said, the clearest kind of different molecules. So methylacetylene, almost all of the emission is actually coming from very large scale structures. While methyl cyanide, you have almost all the emission coming from a very compact structure, so really from the hot core itself. And doing the same thing as for methanol, using, in this case, these rotational diagrams to get the excitation temperature and column density, you can actually compare directly with models that look at how the chemistry should evolve from the outer cold regions into the warm, hotter ones and see how well they do compared to observations. So focusing on the lower panel, what you have is each of these complex organic molecules with respect to methanol. And you have a model, and you have the observations. And this is pre-ALMA, so we have to put the observations in pretty large bins. But at least in the inner part, there is some resemblance of similarity between the models and observations. But there's clearly, the models are clearly missing something once you come to the cold outer parts. And this is maybe not too surprising, since these models were really developed to explain these hot cores, where you have a lot of this bright emission coming from the center, and they have not really been updated to include these discoveries of much colder complex molecules. So here there's definitely room for improvement. And I would argue that the way that you do get this improvement is by, is through basically two different pathways. One is to see really in a more statistical way when these molecules show up. And that's something we're starting to do towards more low-mass protostars. And this is really thanks to, I say, technological development that we now can get with something that the ERM30 meter, we can get 60 gigahertz of data at the same time, which means that we can afford to go very deep and see some of these very weak transitions of these complex molecules also towards cold sources. But what I really wanted to just spend a couple of minutes on is that the other way of improving our knowledge of this chemistry is, of course, to go to the laboratory. So this shows the setup as it looked like the laboratory setup that we had in Virginia until it was taken apart about 2 months ago, and now it's sitting in storage somewhere until the new lab is completed. But it's this kind of setup is designed to look really at the processes that drive the ice chemistry and ice physics in the interstellar medium, which means that you have to get a few things right. So this is an ultra-high vacuum chamber, which means you can get down actually almost to you can get down to the kind of pressures you have in a protoplanetary disk actually quite readily. And then to build up these ices, you also need, of course, to be able to get down to rather low temperatures. You need to have the right kind of radiation sources and the like. But I think that's clear what we can do. I think it's actually clearer in this cartoon where it is that we can do what makes these kind of experiments so special for astronomy. So I mean, normally in astronomy, we're kind of left with what nature chooses to give to us, which can sometimes be rather frustrating. But what we can actually do in astrochemistry is really take the problem into the lab and take it apart. So in these setups, we are pretty good at building up the kind of ices we think exist in the interstellar medium, but we can manipulate them in different ways. We can make them, these ices, in different thicknesses, porosities, compositions, and see how that affects the ice chemistry and ice physics. We can manipulate them with all the kind of things we expect to play a role in interstellar mediums, different kinds of radiation, temperatures, what have you. And then it's much easier to observe what's going on in the lab compared with observing something that's going on many parsecs away. So we can actually really look at the microscopic processes that drive desorption, both thermal and non-thermal, that drives diffusion, so reorganization of these ices, and of course that drives chemistry. And I think here is really where we're now, I think actually already starting to get an idea of what this very cold complex chemistry is that was missing from these models. And one of the things, I think one of the most relevant results that we have had, or like most relevant experiments for this talk that we have done, is actually looking at methanol ice and what happens with methanol ice when you expose it to radiation at different temperatures. So, as you might remember, I said that the CO snowline is very important chemically because it produces methanol ice. And the reason that methanol ice is of such interest to people that care about what kind of organics you end up with on planets is that taking methanol ice and then really taking it apart into as many different parts as you can. It's one of the most efficient ways to form many of these complex molecules that we actually do observe in hot cores and now also in these cold regions. And with that positive message, I really just want to leave you with a few conclusions, which is, I think that both from observations and from theory and also from laboratory work, it's clear that snowlines can play an important role on like several different axes at once, both when it comes to planet formation efficiencies, when it comes to their bulk composition, and also when it comes to chemistry that sets what kind of trace compositions that you get on planetary surfaces. With ALMA, we can actually now start to observe them directly, which is very, very exciting. But it is going to take developments in chemistry as well to move away from just imaging the CO snowline and going to the other snowlines that we think are at least as important for planet formation. And I guess the final point I want to make is that ice chemistry is obviously really important, both for these large-scale processes of planet formation and also when it comes to trying to predict which kind of planets that are good potentials to start forming life in addition to our own. And with that, thank you for your attention.
So thank you very much for a very interesting talk. As I said, very close to my part, so I would have tons of questions. But I, of course, leave it to the students first. They should start. So maybe we can turn on the light a little bit. The students, questions? Let's see.
So aside from the CO snowline, what other snowlines do you like to look at first?
Well, I think the one you would really want to get to is water. In ours, if any snowline was important in the solar system for planet formation, it seems to have really been the water one. That one is tricky because for two reasons. One is that it happens so close to the star. So it means that even with ALMA, we're actually pushing ALMA to be able to get to it. But also because once you get that close to the star, the chemistry basically gets messier. So finding a unique tracer of the water snowline, we're working on it, but it's not obvious that it's going to be trivial. But in the meantime, things like CO2 would be very interesting for sure. That might be one of the most important ones in some systems. And also the nitrogen-containing ones, so the ammonia and N2 snowlines would be the ones from sort of more chemical point of view that you want to get to.
Another student, Mordecai.
I had that down where you could have.
Okay, that's okay.
Somewhere in the middle. A recent mechanism was involved to explain, let's say, these complex organic molecules in the gas phase was reactive desorption. Do you see a way how to constrain, let's say, the efficiencies there, theoretically, and I don't know if it will be ever possible in the lab?
Yeah, no, so one of my postdocs and I are actually trying to think about the experiments to be able to do that, and to, so we're sort of in the design phase, as we're waiting for the laboratory to be built. There are some experiments that suggest that you have a very high efficiency for that. Those measurements were somewhat indirect, which is why we would come up with a more direct mechanism. But I mean, what you want to do is basically, I mean, like a very simple example would be to have CO on your, grain equivalent, which in our case is a window, and then bombard it with hydrogen, and then measure if any methanol or formaldehyde comes off as the hydrogen attaches itself. The problem is that we think you have to have a very good mass spectrometer very close to the surface to be able to pick up that signal, and that's actually what we're designing to be able to do. So we hope to be able to either measure it or put very good limits on it, and it should definitely be possible.
Maybe now can all ask questions.
Yeah, I just want to comment and ask a question. There was a theoretical paper by our former student, Eric Hurst, where they tried to put this enhanced reaction desorption efficiencies in chemical models in order to explain the presence of constant cold low-mass high-mass star objects, and they came up with the result that you need about 10% or so, and plus enhanced differentiation and efficient dissociative combination of the complex molecular ions to be able to explain this. And these two things seem to be unlikely, well, or hard to do, I guess, in reality, because from other constraints we know that the chemical reaction, chemical dissociation cannot be sufficient. It has to be a few percent, otherwise we have a problem to explain the observations of well-studied cores like this one. So it's a bit of a problem now. So I guess it's better to attack this problem from a laboratory point of view.
I concur.
Do you have other questions?
Yeah, I mean, I just wanted to comment on this never-ending story about the origin of Earth's ocean water. And we made a study with our another student, Tobias Albertsson, where we tried to take dynamical solar nebula model and put this deuterium fractionation chemistry into it and studied how the water would be formed in both gaseous and solid phases, and then came to the conclusion that dynamics might have been important for that first, and second is that while you could form rather water-like differentiation for water ice on the cometary forming zone, it seems that the better source of water would be the carbonaceous asteroids. And the reason being that if you would take just the cometary water, which might have the proper differentiation ratio, the comets would brought a lot of noble gases to the Earth's atmosphere, although we have a lot of argon, right?
Okay, Steve, I think we should not have another talk. So.
Yeah, but that's still a problem. What's asteroids or comets, and it's not clear, it's just a comet.
So I think it's very important to realize that.
Yeah, and I just said planetesimals have been a bit more general. It just looked more like a comment on there, but I totally agree with it.
Okay. So in magnetically active zones, current sheets can produce local temperature fluctuations with as much as a factor of 2. Is there any way that we can, I'm sure that has chemical consequences, and has any sort of temperature fluctuation yet been included in the models?
Not in disks, as far as I know, but there has been in protostellar models, which is, in some sense, is a similar problem. It's just instead of a disk, they assume a spherical envelope. But the reason it's been included is there are a couple of different observations that suggest that the current temperature structure of these envelopes have not been there always, but you have had temperature fluctuations for different reasons. And there are two observations that are, I think, very convincing. One is that you see evidence of Cl adsorption to much larger radii than it should be, and of other molecules as well. And the other one is that when you look at these ices that you see towards protostars, you sometimes see that they have been thermally processed in a way that cannot be explained by the current thermal structure. So there are ways you can use chemistry to look at the sort of past dynamical history, which I actually think is going to be one of the most interesting ways to use chemistry, where you really have no other choice than to look at how the mismatch between chemistry and the current physical structure. I think
just to make clear, local intermittent heating regions. So
yeah, exactly. So basically what you can see is if you had a spike in the heating for some reason, you should have probably gotten rid of all the CO into the gas phase. And then there is a time, it takes time for the CO to then, freeze out again.
Yes.
So that's how you can see that, for example.
So it's a great pleasure to have a new director at the MPE Garching with us, actually establishing a new astrochemistry group in the Max Planck Society. So ask your question.
I just want to mention that we have done some models not for this type of heat-oriented disk, but some earlier phases disks that we don't yet know if they exist. But however, we put some chemistry on that, and these disks are self-gravitating, and they develop some spiral structure and then shocks.
got coherent structures which would imply gravitational instability, or the same signatures with sort of diffuse emissions that would imply some sort of MRI type behavior.
And you might even be able to see opacity differences in the dust if you're really lucky.
You still have to solve the debate of these disks exist in these spaces. There's a very strong debate about it. In case,
yeah, I think my question is sort of already half addressed. So I think for the water snowline, I mean, it seems, I mean, we always think of snowline being at a certain location, right? And for the water snowline, it should be somewhere between Mars and Jupiter. But the snowline will evolve in radius, right? If we assume that the viscous heating idea is correct, right? If there are other ways of driving accretion in a disk, maybe the energy is not being deposited in the midplane somewhere else. So by measuring the snow line, you could also maybe tell if the idea of viscous disks is correct in the first place.
So I was up in Toronto just a couple of weeks ago, and one of the people I talked to there, one of the ideas we had was basically using the sharpness of the snow line, which is something that we can estimate, at least eventually. We have multiple transitions of the same molecule, to use the sharpness of the snow lines to basically look at the turbulence in the disk. So you're very close to that idea.
actually, we have an ALMA project measuring turbulence directly using heavy molecules. We are sitting on the data, trying to deduce this now, and we also got a monoproposal accepted. So we hope to get also direct measure of turbulence using heavy molecules. I actually have another question. I mean, there is a big puzzle. If you analyze the carbon budget in the refractory cranes and solar system, it's very low. It's only 5 to 10%. If you go to the interstellar medium, I mean, 50% of the mass is in these carbonaceous material. You have your own personal proposal to solve this problem. I know, of course, Ted Bergen is just burning carbon, but that proposal has a number of problems.
So I do not have my own pet theory, but what I do think is actually more important is come up with an observational test of said pet theories. And one of the things that I have been toying around with Ted is actually what kind of isotopic ratios that you should get that might differ for if you're actually burning off carbon grains one way or another versus just gas that's being transported inwards in the disk. And I think so I guess that's the angle that I'm more interested in trying to figure out with one of these theories what the observational signatures of that should be so we can test them.
I'm actually asking this question because we are running a chain model where we actually assume carbon-oxygen abundance to predict the abundance in planetary atmospheres. And this parameter is just decisive for that, you know, and we really need to understand this carbon budget in order to make the predictions for planetary atmosphere compositions. And therefore, I'm really very much interested in this. I actually have a comment, and that relates to your experiment, because you had this very nice substrate, and then you had ice on the substrate.
Yeah.
But actually, your substrate may be a carbon-containing material. So we actually did an experiment to irradiate ices on a carbon substrate, and then you start to initiate diffusion of carbon atoms into your ice mantle, and you actually burn in this way the carbon, and you form CO, CO2 in complex molecules. And because we have irradiation going on in these environments, that may be an important channel as well. So in other words, the substrate may not be inert.
Yeah, no, so you definitely want to, I mean, I'm definitely with you that ideally you want to try different kinds of substrates and see when they have an effect and when they don't. So the only time we have tried a lot of different substrates was in our ice photodesorption experiments, and then we found it didn't have an effect, but that's maybe not too surprising because we think the photodesorption is really active in the top layers.
Yeah.
But once you get to the chemistry, I think you probably want to start with the inert substrate to figure out what is purely due to ice chemistry. But I'm totally with you that, of course, you want to test them with both silicate and carbonaceous substrates to see what effect they have.
Okay, are there any other questions?
Only just a small comment. Early in your talk, you made a small remark, kind of somewhat playing down the importance of the ice lines with respect to the view from the solar system. I think that's no longer needed because the close-in giant and exoplanets are actually the uncommon case. So I see where it comes from.
They're definitely uncommon case, but I think we do not yet see those systems with this kind of structure as being common. I mean, I'm hoping we will, because I would really like for snowlines continue to be important. We do have sort of rocky planets, and then around 4 or 5 AU have a gas giant. So that was all what I meant. Not that it's ruled out by exoplanetary observations, but that it's not something that you would obviously have thought of if you see the collection of exoplanetary systems.
You do see a big pileup of ring velocity surveys, so you pile up the gas planets out at.
But it's 1 AU. I thought it was around 1 AU or 2 AU. So it's a little bit too close in what I would like to have.
Okay, any other questions? If not, then I would like to thank Karin again.